Swayam Prabha. Digital India. Educated India.
Okay, welcome to the lecture number 9. So, we have discussed about the two particle system. So, in that discussion we were confined to deriving the constant of integrals, okay. And in that way we have been able to identify only 10 constant out of 12. Okay. So, in this lecture we are not going to discuss further on that until unless we go into the three body system or the three particle system. Now, we look into the relative motion of these two particle system, just like say the sun is there and the earth is there. So, how the sun and earth motion will appear, okay. As looked from the sun or either as looked from the earth, both way it can be described. Okay. So, again starting point is the same as we have written m 1 d square r 1 by dt square. So, this is equal to minus m 1 m 2 g by r 1 2 whole cube. I will draw the figure here again. This is m 1, this is m 2, r 1 2, this is r 2, this is r 1. Because here on the particle 2 the force is acting in this direction, which is opposite of r 1 2. So, therefore, the minus sign. So, this can be rewritten as d square r 1 by m 1 we will eliminate, because we are trying to look into the relative motion. So, this is m 2 g divided by r 1 2 whole cube r 1 2 . Now, we are looking for the here relative motion of 2 with respect to 1. So, relative motion of particle 2 with respect to particle 1. If we do that, so we need to write it then like this, subtracting equation 1 from equation 2. So, from here we are subtracting this. So, on the right hand side then we will have m 1 g divided by r 1 2 whole cube times r 1 2. This comes with minus sign. So, this is minus sign, and then subtracting from this part. So, this is minus m 1 g divided by r 1 2 whole cube r 1 2. This is m 2. So, g r 1 2 divided by r 1 2 whole cube, this goes as common, and we get here m 1 plus m 2 with a minus sign. Okay. And the left hand side we can write as d by dt square r 2 minus r 1 minus G R12 or M we will include here first, G M1 plus M2 divided by R12 whole cube times R12, and the minus sign is there, and R2 minus R1 is nothing but R12. So, this is R12 plus G M1 plus M2 divided by R12 whole cube Okay, so, this is the equation of relative motion of particle 2 with respect to particle 1. Okay, remember that we have written the equation of motion of each of these two particles in inertial frame. Okay. Directly we have not taken this, and with respect to this we are started writing the equation of motion. If you do that, that will be absolutely wrong. Okay, doing that approach. We never do like this, because we are trying to formulate the system equation in terms of we are trying to write the equation of motion in inertial frame. Okay. It may happen in certain cases that you write the equation and it turns out to be the relative motion with respect to another particle directly, and it is turning out to be a right one, but that happens only under very special circumstances. So, that I am not going to discuss that that part. You can refer to the Sims book, Engineering Mechanics by Sims, and go toward the end chapter on the rigid body dynamics. So, there those things are discussed, and also here in this attitude dynamics course on satellite attitude dynamics for the MOOCs course, there also I have discussed those topics. So, there here I am not going to include all those things. So, the way is we are proceeding, we are writing the individual equation of motion in inertial frame, and then subtracting them to get the description of how the particle 2 it will move with respect to particle 1. Okay. So, here R12 I will simply write as R for simplicity purpose, so that I do not have to carry this subscript. So, the above equation can then be written as here dt square plus G and M1 plus M2 G M1 plus M2, this we are going to write as mu. So, therefore, this becomes mu by R cube R equal to 0, and if you remember this kind of the equation, this looks like as the form of central force motion under under gravitational acceleration. So, a particle which is moving, a big particle is fixed here, okay, and another small particle is moving here. So, under that circumstances we got this kind of equation. Okay. So, the relative motion it looks like the same thing, like one particle is fixed, another particle is moving around this. The same way, if I reverse the sequence, that if I have this equation and reverse it, rather than subtracting, writing in terms of I am looking for then say the particle 1 motion with respect to 2. So, this is the reference frame, this is M1 and M2. So, then I can describe it like this, okay, particle M moving about particle 2. So, if you do that, again you are going to get the same sort of equation here, format will not change. Okay. So, this constitutes our basic equation, and we know solution for this. Okay. So, this is our equation of relative motion. Okay, and using this all the properties we have developed earlier. So, those can be developed here also. So, I will quickly do that without discussing much. So, after replacing this, so taking cross product, let us name this as equation 1. Here we have 1, 2, 3, 4. This will name as 5, this as 6, and this will name as 7. So, taking cross product with R on both sides of equation 7. This is bits repetition of the previous thing, but therefore, I am going to do it quickly. Okay. So, here in this case dt square plus mu by r cube r, this equal to 0, and what we see from this place, this is r cross d square r by dt square, this equal to 0, because r cross r this will vanish, and you remember that this can be written as r cross dr by dt, this equal to 0, and this implies r cross v, this equal to h, a constant. So, what it says, r cross v, this equal to h, a constant vector. This says that relative motion of particle 2 with or the motion of particle 2 with respect to particle 1 takes place in a plane. Okay. So, motion of particle 2 with respect to particle 1 takes place in a plane. So, this is one property. So, we will write it as A. Similarly, if we take dot product, so as earlier we have done, so we will get the energy is a constant. So, dot product with r dot d square r by dt square, as we have done earlier. This is again repeating, this is repetition of the previous thing. So, therefore, I am going quickly taking dot product on both sides, product with respect to r dot, which is nothing but v, this is nothing but v with respect to r dot on both sides. We are discussing the elementary things. Okay. Until unless we are aware of all these things, we cannot go into the advanced topics. So, from here we have r dot dt square plus mu by r cube, this equal to 0. Okay. So, this is your v. In this format we can write this as v dv by dt plus mu by r cube, and here this we will write in this format r dot, we will write it like this. So, this part, instead of writing it here like this, let us write it in a simple format v v dot. Okay. And we know that this quantity is nothing but d by dt v dot v, and this quantity is also nothing but 1 by 2 d by dt r dot r, right hand side 0. So, this can be written as d by dt v square divided by 2 plus mu by r cube r square divided by 2. D by dt we have missed here. D by dt r cube. So, can we bring this term together like this? So, if you look into this term, this is mu by r cube and this gets reduced to 2 r dr by dt divided by 2. So, this 2 cancels out and we get here mu by r square dr by dt. So, this is nothing but d by dt minus mu by r. If you differentiate it, you are going to get this quantity. So, this says that I can write this term as mu by r, and once we integrate this. So, this implies v square by 2 minus mu by r, this is a constant. So, what we have got v square by 2 minus mu by r, this is a constant, and we can write this as E or E prime, the symbol we use it. So, this is the energy per unit mass. So, in what sense? It is a very important to consider what exactly they are implying. So, this is the v here, it is appearing, this is the relative velocity of 2 with respect to 1, and therefore, this is indicating, this term is indicating relative kinetic energy. This is not absolute kinetic energy, relative kinetic energy. Similarly, this mu by r term which is appearing here. So, remember that this r is nothing but r 1 2. Okay. We have replaced this r by r 1 2 while discussing the in this place the equation of motion. Okay. So, this is the relative kinetic energy in a relative sense. No, this is not in an absolute sense. Okay. If the previously, if you remember that we have written 1 by 2 m v 1 square plus 1 by 2 m 2 v 2 square in the two body problem. So, there this was the absolute kinetic energy. Okay, but here this is appearing as relative kinetic energy, and this is the corresponding this particular term, the potential energy term with respect to the first body. Okay. So, therefore, this says that T plus u this equal to E, a constant. Again the same kind of conclusion we are deriving what we have done for the one body problem. The two body problem also we will look into the system equation, it is a relative motion. So, this gets reduced into the same format. Okay. So, Kepler's law also we derived using the equation. Using this equation we have derived all the 3 Kepler's law. Okay. So, that means this is valid, the whatever we have done earlier. So, that is also valid here in this case. Okay. So, therefore, whatever we have done in the previous lectures, so the same thing is applicable here, and we can just summarize rather than working out the whole thing, we can summarize. So, time period here in this case, this will be 2 pi a q by mu, where mu is g times m 1 plus m 2. And while writing here h, if you look here in this part, so this of course, we know that this can be reduced to r square theta dot equal to h. Okay. So, r indicates the distance of the r is nothing but equal to r 1 2. So, distance of particle 2 from the particle 1. So, this appears as angular momentum of the particle 2 as if the particle 1 is at rest, okay, because we are taking here it in the relative sense. So, this way we are describing. Okay. So, here v is not the absolute velocity, this is the relative velocity, and therefore, h is not the absolute angular momentum of particle 2, because this is a relative velocity, and therefore, this is also relative angular momentum. So, all the terms we remain very much clear about what we are writing and what we are doing. So, this was your the third Kepler law, and in the second what we had a dot, this is a constant which we have written as h by 2. So, that is also valid here in this case. If you take this equation and work out this particular part, so you get the same solution. Okay, that is what we have done. This is particle 1, particle 2 is here, it is moving from this place to this place. So, this is r, which is nothing but r 1 2. Okay, this angle is delta theta, this is at time t and this is at time t plus delta t, r 1 2 equal to r t plus delta t, and from there then taking this area and its a rate of change, we have derived this part. So, this part will come. So, I am not going to work out this, you can do yourself, these are very simple things to work out. Now, look into this t, this is 2 pi a q by mu is g times m 1 plus m 2. Suppose we consider the Sun Earth system. So, in the Sun Earth system, A is known, it is a measured. distances of the stars, they are determined using the parallax method. You can find in book of astronomy or even in BSc level any astronomy book if you pick up. So, you will find it. So, this semi major axis is known. I can assume that m2 is the mass of the earth and m1 is the mass of the sun. So, if m1 is much greater than m2, the above equation will get reduced to this format aq by g times m1, which is nothing but 2 pi aq by mu under root, where mu equal to g m, m1 is nothing but the mass of the sun, m earth. So, you can see that it appears like if the system about with respect to which you are trying to describe the motion, it is a very heavy one. So, you can assume it to be the fixed, and the second mass moving around that, and the time period, then it is given by simply this equation. So, if the time period is known, say in the case of the sun earth system, this time period is known, and therefore, from there m1 can be computed. So, you can see that this will be t by 2 pi square equal to aq divided by mu, or mu equal to aq times 4 pi square divided by t square, and this is g times m1. So, m1 by 4 pi square divided by t square g. So, from here the mass of the sun will be known. So, this is one way of describing the motion of the two particle system. Now, one very important thing I would like to point out. Say in the case of the sun earth system, this is not only the sun earth, but the other planets are also present, but let us forget about the other planets. In the sun earth system, the center of mass lies somewhere inside the sun. So, this is here sun and this is earth. So, both this the earth and the sun, they are moving about the mutual center of mass, which we call as the barycenter. Okay, so, sun is also this center of mass, this is the center of mass of this sun. So, this will go in a circle like this, circle or ellipse, whatever you tell, and this will also move about this point. Okay, so, and they will always maintain same orientation. So, this will come to this point, and from here this will go to this point. But if you are looking in the relative manner, means you are looking with respect to the center of the sun, how the earth is moving. So, whatever we have done on the in this on this previous pages, all this derivation we have done, see this, all these are things are applicable. Okay, relative motion basically we have described. Okay, this is the relative motion. So, this is applicable once you are describing the motion with respect to the sun, but it is possible and it is also prudent that you can write the equation of motion, say this is m1 m2, this is r12, this is r2, this is r1. Okay. So, somewhere your barycenter, it is lying here in this place. So, this is your center of mass, and this location you know. this is RCM, because if you R1 times M1 and R2 times M2. So, this is RCM M1 plus M2. So, rather than describing the motion with respect to this M1, also I can describe the motion with respect to the center of mass. So, in that case what we need to do? We proceed in the same way. We write here M2 times dA square. Now, here I will be describing with respect to the center of mass. Okay. So, if I describe with respect to the center of mass, then we have to take this distance. Okay. So, this distance, how much this will be? dA square r by dT square. So, how this particle is changing with respect to the center of mass? So, this will be R2 minus RCM, and then the force acting on the system, what is this? This is because of the mass 1. So, this is minus G M1 M2, this is acting in the opposite direction, divided by R12 whole cube and unit vector in the R12 direction. This is the way of then writing. Similarly, if you want to write the equation of motion for 1, so this will be written as dA square by dT square times R1 minus here RCM, okay, minus G M1 M2 R12 whole cube. Now, here in this case R12 vector we are taking here in this direction. Okay, this is the R12 vector direction. So, you can see that I will write it with R12, but this will come with a positive sign. So, right hand side does not change, because this is the force term. Okay, force term does not change. What is changing in the even in the absolute motion, once we were considering. So, at that time also on the right hand side we got the same term. Okay. Here we are taking the motion with respect to the center of mass. So, the same thing is appearing, okay, nothing different, and if you add them. So, you can see that what is going to happen. Adding also, if you subtract, so you will get the same relative motion shape. Here in this case we write as M2 we can divide on both sides. So, here if we say if we M2 we divide on this side and M2 we divide on this side, M1 we divide on this and divide on this. So, what this will be? The relative motion then will appear as d by dt square R2 minus R1 if we subtract these two. And on the right hand side similarly we have, if we are subtracting from this one. So, they will add up, and on the right hand side then you get minus G M1 plus M2 divided by R12 whole cube times R12. So, we recover the same equation. So, using the with respect to the center of mass, because center of mass, and why we can write equation with respect to the center of mass directly, because center of mass is non accelerating here in this case. So, if I fix a frame here, this will constitute an inertial reference frame, and therefore, I can write equation of motion with respect to the center of mass, or either in the center of mass frame, which we call as the barycentric frame, barycentric frame. So, I can write directly the equation of motion in barycentric frame, okay, without hesitating, because this constitutes an inertial frame. But if you fix a frame here, so or either you fix a frame here in this place. So, this is not constituting an inertial frame, this is not constituting an inertial frame in itself. So, we will not take that approach, we go through a very right method, so that we do not do any mistake at any stage. So, So, I will stop here and we will continue in the next lecture. Thank you very much.